In this section, we're going to look at solving more trig equations, but this time specifically using some of the identities that we've learned about so far in this class. So over on the right here, I just put a number of these identities up. Hopefully these are all ones that we know already, or at the very least, in the case of the Pythagorean identities, hopefully we've got the one on the left here memorized by heart, and then we can derive the other two from it. And so here in example 1, I want to solve this equation, 2 sine squared theta minus cosine theta minus 1 equals 0. And really it looks a lot like the equations we've already worked on solving that are quadratic in form. I guess if this was a cosine here, I'd feel really good about it, because I'd have 2 times the cosine squared of theta minus cosine theta minus 1. And so I could think of the cosines like they were x's essentially, and use my techniques for solving quadratics to solve that, and then just realize that, okay, well, my x is really cosine, and then go from there. So, we've done that before, but here it's a little different. I've got different trig functions, okay? But what I do have at my disposal is our Pythagorean identity here of cosine squared plus sine squared equals 1. So because of this identity, we also know that the sine squared is equal to 1 minus the cosine squared. So that right there is our ticket to, instead of having an equation that's got sines and cosines, that'll allow me to write this equation so that it has only cosines involved. So this will be 2 times, instead of sine squared, it will be 1 minus cosine squared. And then there's the rest of it, cosine theta minus 1. All right, so let's clean this up a bit. We've got 2 minus 2 cosine squared theta minus the cosine of theta minus 1 equals 0. And so we can have some like terms we can combine. So this will be negative 2 cosine squared theta minus cosine theta, and then 2 minus 1 is positive 1. All right, now the only other thing I would say here is I always tend to like my leading coefficient here on the square term to be positive. So I might kind of be inclined to multiply both sides by negative 1, which of course doesn't do anything to 0. So that would allow me to just have that first one positive, 2 cosine squared theta plus the cosine of theta minus 1, distributing that negative all the way through, equals 0. All right, so at this point, this is definitely that type of problem that is quadratic in form. And so you have options at this point. We can try to factor it. If you're suspicious that factoring might not work, you can always use the quadratic formula. I think it's always nice to take a shot at factoring it. So if it does factor, it would have to have the form 2 cosine theta as the first term and cosine theta as this term equals 0. And if that was to work, since there's a negative 1 here, I'd have to have one of them be plus 1 and one of them minus 1. So let's just try putting plus 1 here and minus 1 there. And if I check the outside and inside, 2 cosine theta minus cosine theta gives me 1 cosine theta. So that does give me my middle term. So it looks like this works. So this leads me to say that 2 times the cosine of theta minus 1 equals 0, or the cosine of theta plus 1 equals 0. All right, so I can, of course, add 1 to both sides here. 2 cosine of theta equals equals 1, and of course dividing by 2 on both sides leads me to say the cosine of theta is equal to a half. And then of course here we're saying that cosine of theta equals -1. Okay, so we're set up rather nicely here, but we've got lots of possible solutions here we've got to keep track of. So let's focus on the cosine of theta equals a half first. Okay, so maybe sketch a little unit circle over here. So when does the x value on the unit circle equal a half? Well, that should happen right about there and right about there. Okay, and so we should recognize that as pi over 3 and negative pi over 3. Or if you'd rather, 5 pi over 3 here, either way. So we get theta is pi over 3 plus 2k pi, or theta equals negative pi over 3 plus 2k pi. And then, of course, we've got cosine of theta equals -1. All right, so when is the x value on the unit circle -1? Well, of course, that happens right here, right? Right there at pi. All right, so theta is equal to pi, and then, of course, plus 2k pi. So that adds one more piece to the solution. Oops, plus 2k pi. Didn't mean to have that line right there. So we of course have infinitely many solutions as usual, but we've got 3 different statements that we have to make that of course each involve infinitely many solutions. Okay, but the key here is we treated it like a quadratic in form problem, but we realized in order to really apply that idea of having a problem that's quadratic in form, you got to have all the trig functions the same, and so we set to work in doing that using the Pythagorean identity. All right, so let's look at this example where we have 2 times the tangent plus the secant squared equals 4. Now, we're looking at this. It seems like it's also perhaps quadratic in form, but again, the trig functions don't match one another. And hopefully when you see secant squared, you're immediately thinking of a Pythagorean identity, because one of our Pythagorean identities does involve tan squared and secant squared. But the thing that we want to remember is exactly how that all goes together, and let's say just for a second that we forgot. Okay, I've forgotten exactly what the tan squared and secant squared identity looks like. So just remember, if you can put down the one that we're definitely supposed to have memorized to the point where we're dreaming about it, if we can write that down, then we can always get the other Pythagorean identities if we just divide by either sine squared or cosine squared. And since I want the one that involves tangent, I think that I should divide the sine by, or the sine squared by the cosine squared. So of course I got to do that in every term to make that legal. All right, but what I get, of course, is the tangent squared plus 1 is equal to the secant squared. All right, so I've got a nice substitution that I can make here. This secant squared can turn into tan squared plus 1, and so that's going to be the key for me to be able to rewrite this in such a way that I can treat it as quadratic in form. So I have 2 times the tangent of theta plus, instead of secant squared, I've got tangent squared theta plus 1, and that equals 4. And of course, if it's quadratic in form, it's kind of nice to start with the square term. And it's of course also the thing we want to do is to get one side equal to 0. So subtract 4 from both sides and put a -3 there. All right, and so it's worth investigating whether we can just easily factor this. So the tangent of theta would, of course, have to go first in both of these factors if it works out. But then my -3, okay, well, one of these has to be 3 and one has to be 1, and they have to be opposite signs. And because the middle term is positive, I would know to put the plus with the 3 and the minus with the 1. And in fact, that works out great. The outside is 3 times the tangent. The inside is -1 times the tangent, which would give me +2 times the tangent. So this factorization works. So I've got two different things going on here. The tangent of theta -1 equals 0. And then I've got the tangent of theta plus 3 equals 0. So here the tangent of theta is equal to 1. All right, now let's think about this for a moment. Is this a special value? Is there a spot on the unit circle where the tangent equals 1? Well, sure there is. One of our special values, right? The tangent is going to equal 1 where sine and cosine are equivalent. So sketching a quick unit circle here, sine and cosine are exactly the same right here at pi/4. So I can give an exact answer to this. I can say theta is equal to pi/4, and let's remember that the period of tangent is not 2 pi, it's just pi, right? So we're going to say plus k pi. And you know that, of course, they're also going to be equivalent at 5 pi/4, right? Where it's -√2/2 and -√2/2. And, of course, adding pi to pi/4 gets you 5 pi/4. All right, so this encompasses all the solutions produced by this particular factor. All right, but now let's look at this one. We're saying the tangent of theta equals -3. So is this a special value? In this case, the answer is no, it's not. You know, what are we looking for when we're looking for special values? We're obviously looking for 1 or -1, 0, but then we're also looking for √3s to show up, right? Either square root of 3 or 1 over the square root of 3. Those are going to indicate we have special values on the unit circle. But here, -3 is not one of those. So here I'm just going to have to do an approximation. So I know that theta is going to equal, is going to equal the inverse tangent of -3, but again, plus k pi, right? Because that's the period of tangent. And let's go ahead and get an approximation for that so I know about where that goes. So my approximation here is about -1.25 plus k pi. So putting all this together, we say theta equals pi/4 plus k pi, or theta is approximately -1.25 plus k pi. And of course, where k is any integer. All right, let's look at another example here. So I have 2 times the sine of x equals the tangent of x. All right. So looking at this, you know, again, we have 2 different trig functions here, but no squares. So at that point, I'm kind of thinking that the Pythagorean identities aren't going to do me a whole lot of good because I don't have sine squareds, cosine squareds, tangent squareds. If I did, then maybe I could use one of those Pythagorean identities. So I guess maybe the next best thing would be to say, well, I know that tangent can be written so that it has a sine in it. So maybe a natural thing to try might be to say the sine of x, 2 times the sine of x equals the sine of x over the cosine x. And I suppose that that gives me another sine, but it also just gives me a cosine. So I still have two trig functions involved here. Um, now, just a little point of order here. Please do be careful not to try to do any kind of canceling of these signs. It's certainly true that if I divided both sides by sine of x, algebraically, of course, the sides would simplify to saying that there's no more signs involved. But don't do that, because what actually happens is you lose solutions that way. So you want to avoid dividing by things that have variables in it. So since that won't work, my suggestion is let's just do the kind of thing we might do if we were solving an equation that had just a regular x on both sides, and that would be get all the x's on the same side first. Okay, so it would definitely be legitimate for me to write this. Right, just subtracting sine over cosine from that side. Now what I can do is, if I've got a sine x in both terms, I can factor that out. So this could be the sine of x times 2 minus 1 over the cosine of x. And this is actually really nice, because the moment that I have it factored into two different factors multiplied to make 0, I can say, okay, either this factor is 0 or this one is 0. And I can just set to work on trying to solve each one. So let's start with this one because it looks much easier. When is the sign 0? Well, the sign is 0 on the unit circle at 0, and at pi, and at 2 pi, and at 3 pi, and so on. So I know that the solution to this is x is equal to all copies of pi. Okay, we can see that right there on the unit circle. So that's really nice and simple. This one might be a little less simple, but I can go ahead and say, well, let's move the 1 over cosine to the other side. So add that to both sides. So I have 2 equals 1 over the cosine. All right, but if 2 equals 1 over the cosine, if I just take the reciprocal of both sides, wouldn't that have to mean that the cosine would be equal to 1/2? Okay, we'll pick things up over here. So if the cosine of x equals 1/2, okay, again we can draw a little quick unit circle. So the cosine equals 1/2 at pi over 3 and negative pi over 3. I believe we had the same equation pop up in an earlier example. So I can then say x is equal to pi over 3 plus 2k pi, or x equals negative pi over 3 plus 2k pi, or the one that we got from over here, from the sign being 0, x is equal to k pi, where of course k is an integer. All right, and so this whole smash here is my solution. All right, one more example. I have the cosecant squared of x equals 2. So in many ways this looks perhaps much simpler than what we've done on some of the other ones. But you know, our knowledge on the unit circle really is most comfortable thinking about sines and cosines, right? So I would suggest that instead of thinking of the cosecant squared, let's think of the sine squared. So that would be 1 over the sine squared of x. is equal to 2. And then this looks a lot like what happened in the last example, right? So I can take the reciprocal of both sides and say that the sine squared of x is equal to 1/2. Okay, now the sine squared of x equaling 1/2, we've got to not have the sine squared equals 1/2 to be able to start searching for special values. We need the sine of x to equal 1/2. So taking the square root, I see that the sine of x is equal to plus or minus the square root of 1/2, right? And this actually is a special value, right? Because what is this? If I take the square root of the top and bottom separately, it becomes 1 over the square root of 2, which, remember, is probably the less often used special value, but is nonetheless the same thing as when we have root 2 over 2. As you can see there, so this is plus or minus root 2 over 2. So what I've done now is the equation I started with now splits into a couple different equations. So on the one hand, I can say I'm going to have the sine of x equaling positive root 2 over 2. And then on the other hand, I'm going to have the sine of x being equal to negative root 2 over 2. All right, so let's think about where these things happen. Okay, sine of x equals root 2 over 2, definitely here at pi over 4, right? So x is equal to pi over 4 plus 2k pi. But it also happens whenever you get one solution for the sine, it happens when you take pi minus the first solution, right? Pi minus pi over 4, which puts me right here. Okay, but that of course is 3 pi over 4. And if I want to be careful about my algebra, this would be 4 pi over 4 minus pi over 4, which of course gets me the 3 pi over 4 I was expecting. Okay. All right, so that's good. I kind of ran into this equation a bit, so put a little dividing line there. All right, so now we can do the same thing here. So when does x equal negative root 2 over 2? Well, definitely it happens over here at negative pi over 4 or 7 pi over 4. You can think of it either way. Doesn't matter how you express it at first here. And then it definitely happens over here. The sign is negative in this spot. And so what is that? Well, again, you can see that it's just equal to 5 pi over 4 or negative 3 pi over 4. But generally, you always say that it's pi minus the other solution plus 2k pi. But of course, that's 4 pi over 4 plus pi over 4, which gets us, again, the 5 pi over 4 we were expecting. Ran out of room there. Okay, so here we got all these, right? And in my picture, if it's bothering you that I have a negative pi over 4 here when all the rest are positive, okay, that's fine. Just change it to 7 pi over 4. It doesn't matter. Okay, and the reason, of course, it doesn't matter is because I've got infinitely many solutions sitting here, right, because of this 2k pi. So I've got all the solutions. But what I would say is, before we finish this problem, is that we can do better than all these different statements we've made. We've made these 4 statements about what the solution is. But let's think this through for a moment. Let's just look at the picture. In the picture, it seems like we go pi over 4, and then we just continue to go multiples of well, excuse me, I should say odd multiples of pi over 4 all the way. So another way of thinking of this is take a starting point here, and then add pi over 2, right? Or 2 pi over 4. So if I go plus 2 pi over 4, right, that gets me there. And if I say plus another 2 pi over 4, that gets me to the next one. Okay, and so you can play this game all the way around the circle. So I can put all 4 of these big solutions together in one condensed nice solution. So what's really going on is that my solution is x is equal to, let's start with pi over 4, and just add copies of 2 pi over 4, and of course subtract copies of 2 pi over 4 to get all the other solutions. And of course 2 pi over 4 simplified is pi over 2. So I would say plus k pi over 2. And so all of that mess above simplifies down to this really nice solution that's easy to write down. So while it's certainly not inherently a bad thing to have solution sets that, you know, take a number of lines to write, sometimes that's completely necessary, do look out for opportunities to simplify it down like we were able to do here.